Hello, everyone, and welcome to today's webinar, Using Chemically Defined Media for Cell Culture. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by FUJIFILM Irvine Scientific. To learn more, visit irvinesci.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the Continuing Education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Dr. Shahram Shahabi, R&D Manager, Cell and Gene Therapy at FUJIFILM Irvine Scientific. Dr. Shahabi, you may now begin your presentation.
Hello, everyone. Thanks very much for the nice introduction. As it mentioned, my name is Shahram Shahabi, and I'm R&D Manager in Cell and Gene Therapy Group at FUJIFILM Irvine Scientific. The title of today's presentation is Using Chemically Defined Media for Cell Culture. At first, I want to talk about the learning objectives of this presentation. The learning objectives will be understand the potential of chemically defined serum-free cell culture media, describe the benefits of chemically defined media, discuss the scientific concerns faced when cell culturing with serum-based media, and learn how to make the switch from serum-based media to chemically defined media. And the discussion topics include a brief overview of FUJIFILM Irvine Scientific, serum for cell culture media, serum-free and chemically defined media, challenges in developing serum-free and cell culture media, building a serum-free medium, and two case studies. Case study 1 is prime XV dendritic cell maturation CDM, and case study 2 is going to be prime XV T cell CDM. So at first, our mission in FUJIFILM Irvine Scientific, for more than 50 years, our mission has been to develop and supply products and services for the growth and handling of mammalian cells, wherever we can contribute to the health and well-being of mankind. Irvine Scientific has been leading innovative projects for more than 50 years. As it's shown in this slide, this company started its work in 1970 by producing classical media and serum. Since then, this company has expanded and also innovated several cell culture media and reagents, including, but not limited to, serum-free and chemically defined media. Irvine Scientific was acquired by FUJIFILM Holding in 2018 and was renamed FUJIFILM Irvine Scientific. One of the important in vitro methods are cell and tissue culture methods that are generally fast, cheap, and reproducible, and also reduce the use of experimental animals. That's very important. To keep cells alive for relatively long periods of time and to evaluate proliferation, migration, and differentiation, a basal medium must be supplemented with several factors. Serum from animals or humans is most commonly used to maintain and proliferate cells. Cell culture techniques, as you know, are used to grow and maintain cells of various types, including those derived from primary tissues, such as stem cells and also cancer tumors. A major confounding factor with cell culture is the use of serum or animal products to supplement media. The most common form of serum supplement are animal-based fetal bovine serum or FBS and fetal calf serum or FCS. A disadvantage of using serum is animal-based products introduce batch and lot variations that can lead to experimental variability. So in this slide, I want to just briefly talk about chemically defined medium. That's the main topic of our presentation today. A chemically defined medium is a growth medium suitable for the in vitro cell culture in which all the chemical components are known. Standard cell culture media commonly consist of a basal medium supplemented with animal serums such as FBS as a source of nutrients and other underdefined factors. Chemically defined medium requires that all components be identified and have their exact concentrations known. It should be free from any animal or human-derived components. Despite the advantage of adding serum to the cell culture media, good cell culture practice or GCCP, that's an attempt to develop a common standard for cell culture methods, recommends to not use serum unless it's absolutely necessary. The implementation of the use of chemically defined media is part of the GCCP. This will decrease the dependence on serum that's a supplement with an undefined and variable composition. So when we consider supplementing cells and tissue culture media with serum, the no unless principle should be applied. This principle says that preferentially the medium should not contain any animal-derived component unless it was proven to be an absolute requirement. Before moving forward, I want to share with you some of the definition in this area, I mean, serum-free and chemically defined media area. So a serum-free component does not contain serum or plasma, so it may contain components derived from serum or plasma. This may include animal-derived components such as bovine serum albumin and other crude protein fractions. Xeno-free products may contain human-derived components such as human serum, growth factor, or insulin, but they don't contain any animal-derived components. Animal component-free products do not contain any animal or human-derived products to the tertiary level. It means raw material handling, storage, and final product manufacture, and also packaging are conducted with a dedicated human and animal component-free facility and equipment. All chemical components in a chemically defined medium have known composition and concentrations, for example, recombinant proteins. Chemically defined medium provides reproducible results, traceability, and regulatory compliance. There are some challenges in developing serum-free cell culture media. As you know, over the last 20 years, investigations into cell functions have identified components which have been useful in the development of modern serum-free cell culture media. However, considering the advantages of serum for cell culture media, there are several challenges in developing serum-free cell culture media. For example, I can say replacing the components of serum, protective effects of serum, for example, against shear stress and pH changes, and cell-specific requirements. So regarding the components of serum, they, for example, include proteins for attachment and carrier, growth factors, hormones, minerals, and lipids. Other than the advantages were mentioned in the previous slide, there are other advantages regarding using serum for cell culture. Serum is a complete media. It contains all components required for cell growth. It increases viscosity, so lesser shear forces rise, and variability of cells is going to be more, and it acts as a buffer. So all of these advantages, they're going to be challenges against developing serum-free and chemically defined media. With time, it's been clear that almost every cell type has its own requirement concerning medium supplements. Different cell types have different receptors involved in cell survival, growth, and differentiation, and they release different factors to their environment. Therefore, a universal serum-free cell and tissue culture medium may not be feasible. Furthermore, by increasing the degree of chemical definition, the specificity of media is increased too. To exclude serum from a cell and a tissue culture medium and still maintain cell adhesion, growth, and proliferation, it's important to include a large number of several components in the cell culture medium. Here, a schematic modular approach for the development of serum-free media is shown as a media pyramid. The bottom of the pyramid contains the basal medium, which includes, for example, DMEM HAMS F12 supplemented with the insulin transferrin selenium or ITS to make adherent cells stick to the bottom of the cell culture vessel. Coating with components of the extracellular matrix should be considered. The next step in media formulation and development is the addition of specific hormones or growth factors. And the tip of pyramid represents increased specificity in serum-free media composition. I mean the addition of lipids, antioxidants, and vitamins. To show how chemical defined media work, I will present two case studies. As the first case study, I will talk about the prime XP dendritic cell maturation CDM. That's a chemically defined and animal component-free medium. This medium has been developed for the in vitro differentiation of monocytes into immature dendritic cells and subsequent maturation to produce mature dendritic cells. Other key attributes of this medium include achievement of high yields of mature dendritic cells with the desired characteristic and functionality, maintains potency of dendritic cells for T cell stimulation, chemically defined, so it's a chemically defined medium, so it means that it contains recombinant albumin but not plasma-derived albumin. It's animal component-free, and it requires cytokine based on the end user's application. Before moving forward with this case study, I want to show you how this medium contributes to dendritic cell immunotherapy workflow. You can see the dendritic cell immunotherapy workflow in this slide. So actually, the monocyte enrichment happens in peripheral blood molecular cells of the patient. So after that, the monocytes going to be differentiated to immature dendritic cells using cytokines, for example, interleukin-4 and granulocyte macrophage colony stimulating factors. And then the immature dendritic cell going to get matured. So then mature dendritic cells will be exposed to antigens as they're going to be primed, and the primed dendritic cells going to be injected back to the patient's body. So in this area, I mean differentiation of monocytes to immature dendritic cells, and after that, maturation of immature dendritic cells. This is where this medium can help and facilitate the process. So the aim of this medium is the differentiation, maturation, and maintenance of monocyte-derived dendritic cells, and also demonstrate a T helper 1 polarized immune response. The performance was measured by maturation and maintenance of monocyte-derived dendritic cells. Total viable cell density was used as a quantitative measurement of media performance. We wanted equal to or even better than benchmarks that we used. The benchmark were a commercially available dendritic cell maturation media and also RPMI plus 10% FPS. While the other indicators, such as cell surface marker expansion and mixed lymphocyte reaction, they used as a qualitative measurement. Negatively enriched CD14 positive monocytes from different donors were cultured in either prime XV dendritic cell maturation CDM, this group, other commercially available medium, this group, or RPMI plus 10% FPS, that's this group. For 6 days, the culture was for 6 days in the presence of GM-CSF and also interleukin-4 to induce differentiation. Then subsequently culture these cells culture for 2 more days in the presence of TNF-alpha, interleukin-1 beta, and interleukin-6, and also prostaglandin-2 to induce maturation for a combined culture duration of 8 days. Resulting cells were analyzed by flow cytometry to measure viable cell density. As you can see in this slide, the yield achieved by prime XV dendritic cell maturation CDN was comparable with those of the other commercially available medium and also RPMI plus 10% FPS. This slide shows what we expected regarding the change in the expression of different surface markers during differentiation of monocytes to the immature dendritic cells and then to the mature dendritic cells. As you can see, the maximum expression of CD14 happens on the surface of monocytes, whereas its expression decreases with maturation of monocytes to immature dendritic cells, and it becomes 0 on the surface of mature dendritic cells. On the other hand, we don't expect expression of CD83 and CD197 on the surface of monocytes. Their expression starts from immature dendritic cells, but it reaches to its maximum level when dendritic cells become mature. Yeah. The minimum expression of CD80, HLA-DR, and CD209 would be on monocytes, and they reach to their maximum expression on the surface of mature dendritic cells. After explanation of the expected kinetics of the expression of the surface markers during maturation of monocytes to mature disease, let's see what our experiment showed. In this experiment, negatively selected CD14 positive monocytes were cultured in prime XV dendritic cell maturation CDM. First, they differentiated to immature dendritic cell, and then the maturation of immature dendritic cells to mature dendritic cells was induced using a standard cytokine cocktail. The results showed surface marker expression profile at day 0, I mean monocytes, day 6, immature dendritic cell, and day 8, mature dendritic cells. As you can see, typical surface expression profile observed when cultured in prime XV dendritic cell maturation CDM. I don't want to go in much details, but it follows what we expected. The other experiment was about the ability of prime XV dendritic cell maturation CDM to generate dendritic cells capable of inducing T cell proliferation. On day 8, monocyte-derived dendritic cells that had been cultured in prime XV dendritic cell maturation CDM were harvested and co-cultured with allogenic CD4 positive T cells plus interleukin-2 for 6 days prior to analysis. As you can see, T cell stimulatory capacity was confirmed by loss of CFSE, which was similar between prime XV dendritic cell maturation CDM, this group, RPMI plus 10% FBS, this group, and two other commonly utilized suppliers, this group. The number of donors for this experiment, there were 3. In addition, flow cytometry analysis demonstrated an increase in interferon gamma expression across 3 different donors compared to RPMI plus 10% FBS and also 2 other commonly utilized suppliers. So these results indicate that prime XV dendritic cell maturation CDM generates DCs that they were capable of inducing T helper 1 polarization. So as the conclusion of this study, I can say prime XV dendritic cell maturation CDM, a chemically defined and animal component-free formulation, is capable of comparable maintenance of viable cell number to the benchmark and other suppliers tested across multiple donors, inducing differentiation of monocytes to immature dendritic cells and maturation of immature dendritic cells to mature dendritic cells, inducing a standard dendritic cell surface marker expression profile, and inducing T cell proliferation and T helper 1 polarization even better than the benchmark and other suppliers. As the case study 2, I will talk about prime XV T cell CDM that launched by FUJIFILM Irvine Scientific as the first commercially available chemically defined animal component-free medium for T cell culture. This medium has been developed to maximize consistent growth of T cell while maintaining their functionality and also therapeutic potential. In this slide, I showed the CAR T cell therapy workflow just because one of the most important application of this medium is going to be using in CAR T cell therapy. As you can see, there are several steps, for example, collection, isolation, activation, modification, expansion, washing and processing, and also administration to the patient. So this medium can be used in different steps of CAR T cell therapy workflow. As I mentioned before, an increasingly important trend in cell culture media for immunotherapy is the move away from animal-derived and undefined components to serum-free and chemically defined culture conditions. Actually, when working with T cells, the advantage of this approach is even more because animal-derived components are variable between lots, and the naturally occurring cytokines and growth factors in them can result in undesirable effects. For example, cytokine and growth factors have been shown to impact growth, phenotypes, and also the potential of T cells to polarize into therapeutic subtypes. Chemically defined media also reduces the risk of introducing foreign agents or impurities from undefined components, thereby chemically defined media facilitating a scale-up to commercial production and the regulatory submission process. I mentioned scaling up the T cell cultures. Bioreactors are very useful tools for scaling up cell cultures. Here you can see 2 bioreactor systems, G-Rex, that's a static system, and quantum bioreactor, that's a dynamic system. There are some benefits for bioreactor. For example, G-Rex got some benefits. It's got increased oxygenation, linear scale up, not feeding required. It depends if we use the M or R series. So it's designed for immune cells and double amount of the resulting cells. For quantum bioreactors, there are some benefits too. For example, oxygenation increase, continuous control of temperature, controlled flow of liquids, control of metabolites, and high cell viability, double amount of resulting cell, and also it's a closed system. However, scaling up from static cell culture conditions like plates, flags, and also G-Rex to dynamic conditions like quantum bioreactors may result in some challenges for serum-free culture cells. One of the most important challenges is the increased shear stress, as you can see here. As before mentioned, serum itself is a protector against shear forces, so this challenge is really important for serum-free culture media. Prime T-cell CDM got some key attributes. For example, it's designed to support ex vivo rapid T-cell growth and viability while maintaining functionality of T-cells. It supports T-cell expansion from PBMCs and isolated T-cells. It's validated to support different T-cell subsets. It supports T-cell expansion without additional serum under chemically defined conditions. It's chemically defined, so it means that it contains recombinant albumin, for example. It's animal component free. It requires cytokines based on end user application. T-cell CDM designed specifically for T-cells, not for general immune cells, unlike other commercial media. And it's the first commercially available chemically defined animal component free medium for T-cell cultures. To evaluate the ability of prime XV T-cell CDM to support T-cell expansion in G-Rexes and quantum bioreactor, an experimental study was designed and performed in FUJIFILM Irvine Scientific R&D Cell and Gene Therapy Group. Current slide showed the experimental setup in G-Rexes and quantum bioreactors. As you can see, the study was done on PBMCs and using interleukin-2 and antibodies against CD3 and CD28. The aim of this study was to show that the prime XV T-cell CDM supports the T-cell expansion in G-Rex system and also quantum bioreactor, at least as good as the available benchmark non-chemically defined media. As you can see in this slide, the CD3 positive expansion was the same by using three tested media in G-Rex system. I mean, by using prime XV T-cell CDM, commercially available Xeno serum-free or XSF medium, and also RPMI plus 10% FPS. So you know that CD3 is a pan T-cell marker. So in quantum bioreactor, T-cell expansion by using prime XV T-cell CDM was obviously better than that of commercially available XSFM. Yeah. Regarding the viability of three media, actually, as you can see in this slide, those three media have a similar and acceptable effect in G-Rex system here. In quantum bioreactors, the viability of cells by using prime XV T-cell CDM and commercially available XSFM was the same. However, the prime XV T-cell CDM has a better effect. As you can see in this slide, CD3 positive fold expansion exhibits a marked increase in hollow fiber bioreactor, I mean quantum bioreactor versus G-Rex. As you can see in this slide, in the G-Rex system, the expression of CD25, that's the alpha chain of interleukin-2 receptor and it's an activation marker, was the same and almost zero amongst three groups. The expression of CD62L or L-selectin and PD-1 marker, that's an exhaustion marker, were also similar amongst prime XV T-cell CDM group, commercially available XSFM, and also RPMI plus 10% FPS group, as you can see here. In the quantum bioreactor, the expression of CD25 was obviously more by using prime XV T-cell CDM and the commercially available XSFM than that of the baseline. However, this marker showed a better expression by using the commercially available XSFM. The expression of CD62L and PD1 was the same by using prime XV T-cell CDM and the commercially available XSFM. You might ask a question regarding the low expression of CD25 marker in all the groups of the GREX system here. I should say these data in GREX system are from day 14 at the point the vast majority of cells are in the resting state and do not express the activation marker, whereas the quantum data, they are from day 9. So we still see some CD25 expression as the cells are still experiencing the effects of anti-CD3, CD25, CD28 T-cell activation beats. In addition, the activation beats in the case of the quantum experiment can't leave the closed circuit, the closed system, whereas the activation antibodies in GREXs are, actually completely removed during the media exchange step. As you can see in this slide, GREX system, the prime XV T-cell CDM increased the percentage of CD8 positive T-cells. However, the increase was slightly less than what happened by using the commercially available XSFM and also RPMI plus 10% FPS. In the quantum bioreactor, as you can see here, the prime XV T-cell CDM increased the percentage of CD8 positive T-cells here better than those of GREX system. Furthermore, the increase of CD8 positive T-cells by using the prime XV T-cell CDM in the quantum bioreactor was more than that of the commercially available XSFM. So we might say that the prime XV T-cell CDM showed the best effect on increasing the percentage of CD8 positive T-cells when it's used in the quantum bioreactors. So cell diameter analysis is a shorter process around for the prime XV T-cell CDM in comparison to the commercially available XSFM medium in the quantum bioreactor. As a conclusion of this study, I will say that prime XV T-cell CDM supports T-cell expansion without additional serum under chemically defined conditions. This medium is capable of supporting T-cell expansion across static and dynamic cultivation conditions. This medium supports expansion of both CD4 positive T-cells and CD8 positive T-cells, but it favors CD8 positive T-cells, and it maintains functionality of T-cells. At the end, I should thank Anastasia Silikova, Supriya Pokali, and Chandana Sharma for their contribution and support for the chemically defined media-related innovative projects in FUJIFILM Irvine Scientific in recent years, and also preparing this presentation. Thank you very much for your attention. I take the questions.
Thank you, Dr. Shahabi, for your informative presentation. We will now start the live Q&A portion of the webinar. I want to remind our audience, if you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. All right, let's get started. Our first question here asks, does using chemically defined media require supplementation?
Thank you very much again. So, actually, yes. Using chemical defined media requires supplementation. There are some general supplementations. For example, some hormones, for example, insulin is going to be needed for a lot of cells. I'm going to say, essential amino acids or other things. But there are some specific supplementation that they are needed for a specific cell. So the question is going to just I'm going to say that short answer is yes, it needs supplementation.
Great, thank you. Our next question here is a two-part question, and this one asks, do you have any experience using recombinant human albumin, RHA? And second part here, what are your thoughts on moving from BSA/HSA to RHA?
So the first part, I should say yes, as you can see the CDM media, all of them, they got recombinant albumin, human albumin. And so if you're gonna have a CDM, or I'm gonna say chemical defined media, you need to use RHSA, and you cannot use, for example, BSA. And our experiments show that, generally speaking, I'm gonna say, they work very well. Recombinant HSA in comparison to, plasma-derived albumin, I'm gonna say, so human or animal sources. Generally speaking, sometimes even better. But there are some suppliers. We saw that their efficacy is not good, so I cannot mention which suppliers here. But there are some suppliers. So when you got something, you should actually make a comparison between what you got, recombinant HSA, and the plasma derived HSA. You should compare it at first, and after that you can move forward.
Great, thank you. All right, next question here. What experience have you had? Oh, excuse me, sorry about that. What experience have you had with CDM in converting anchorage cells to suspension cells?
So actually, yes, we got some experience here, and actually, but not regarding cell therapy actually here, but other area. Yeah, yes, we got some experience, and I can say yes, we can use CDMs for this purpose too. To actually converting the anchorage cells to suspension cells. So yeah, we can use it.
Great. All right, next question here asks, do cells need to go through a period of adoption when they expand in chemical defined media?
Oh, yes, absolutely. They do need, to go through the adaptation period. And there are some, actually different ways and methods for the adaptation. So, yeah, and they do need.
Great. Next question here asks, how can you protect against shear stress and pH changes?
So actually, as mentioned in the slides, serum itself got a very big effect against shear stress and also pH stress. For shear stress, the effects of serum is gonna be more, because of its viscosity. Some studies they show this is related to albumin, and other studies show now it's not related to albumin, so we cannot say anything definite. So I can say for chemical defined media, we can use Plaronic at 68, for example, or other surfactant, but one of the most used is Plaronic. Surfactant, we can use it if it's needed, because shear stress is not a general and universal problem. When you got ordinary cell culture, the shear stress is not actually a very big problem. But where you're gonna go toward dynamic cell cultures, for example, quantum bioreactors. So, or you got a lot of agitations during your cell culture for any purpose, or you should deal with it. As I mentioned, we can use Plaronic surfactants, for example, Plaronic F68.
Great. And I want to thank our audience for these great questions that are coming in here. I want to continue to encourage you to submit these questions. We've got plenty of time here and we'd love to answer them. So let's keep moving here. This next one, how important is it to choose right vessels for CDM conditions?
Uh, Actually, CDM, I gonna say CDM media industry is too young. But as I mentioned, chemical defined media is going to be specific. So we think it's not going to be a specific just for the cell type. So it's going to be a specific for vessel types maybe. So all the time that we produce a CDM media here, we actually use different vessels to make sure that it is going to be compatible with different vessels. So generally speaking, I'm going to say maybe in the future years we find something else that no, this chemical defined media is going to like serum containing media is good for different vessels. But I'm gonna say we should take a look at the scale of the vessels and also the dynamic of vessels. For example, is it plate or flask or also or is it G-Rex or no? Is it for example quantum bioreactor is a dynamic system. So here we try different vessels to make sure. So at this point I'm gonna say yeah. So it's better that you got a CDM, I mean clinical defined media that have been tested for different vessels. Maybe it needs to be customized for different vessels. So that's the knowledge that we got now. As I told you, as I mentioned, because it's a very young, industry. Actually, maybe in the future we find okay, no, you don't need to be worried about the vessels. But at this point, regarding the type of vessels, the dynamic, the scale of vessels, the volume of vessels is better to be tested.
Wonderful. All right, I have another question for you here. This one asks, do cells perform differently in prime XV T cell CDM when compared to serum-contained media?
Oh, actually, no. Actually, they are the same, and we got some feedback from our customers that even in some occasion, this media actually act and perform even better than serum containing media. So I gonna say no. It's gonna be act and behave in the same way.
Great, thank you. All right. Well, thank you again, Dr. Shahabi, for your time today and your important research. We would also like to thank LabRoots and our sponsor, FUJIFILM Irvine Scientific, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.
Thank you very much. Bye.